At this point, I want to discuss the integral test in full. So this is the full version of the integral test. So again, the integral test is going to be something that we'll use to determine whether or not a series converges or diverges. And it turns out we can compare it to an integral for reasons that I described in the previous video. So here's the hypotheses that we need. So we need f to be a continuous, positive, decreasing function. So suppose f is a continuous, positive, decreasing function on some interval from 0 to infinity or 1 to infinity. I'm just going to say from k to infinity. And suppose that f of n is equal to a sub n. So in other words, the function that we're looking at and the sequence are more or less the same. So like the example that we talked about in the previous video was the function was 1 over x squared and the sequence was 1 over n squared. So that's what we're looking at. Then it turns out that if f satisfies all these hypotheses, then the integral from k to infinity of f of x dx converges if and only if, the series from k to infinity converges. Okay, when I say if and only if, this is a statement that goes in two directions. It says if one converges, so does the other. But it also says if one diverges, so does the other. So in other words, the convergence of either both of these both the integral and the sum converge, or they both don't converge. Okay, in other words, either they both converge or they both diverge. So that's what the integral test says. Whatever happens to one happens to the other. We've already seen 1 over x squared. The sum of 1 over x squared converges. Okay, so we've already seen that the sum of 1 over n squared converges to pi squared over 6. And we know that the integral of 1 over x squared converged to 1. So notice that they don't have the same value. All we're saying is that if one is finite, so is the other. If one's infinite, so is the other. Now, let's look at a new example, and let's revisit the harmonic series. So we have 1 over n as n goes from 1 to infinity. And we've already seen that this diverges. But what I want to do is I want to compare this to the integral from 1 to infinity of 1 over x dx. And think about how we would evaluate this integral. This is going to be the limit as n goes to infinity of the integral from 1 to n, 1 over x dx. And we know that that's going to be the limit as n goes to infinity of, if we integrate 1 over x, we'll get the natural log of the absolute value of x, but x is positive. X is going from 1 to n, so x is positive. We don't need the absolute value. And this is going to be the limit as n goes to infinity of the natural log of n minus the natural log of 1. Natural log of 1 is 0. But the point is that this is going to be infinite, because we know that the natural log of n tends to infinity as n tends to infinity. And therefore, this integral diverges, and therefore this this series diverges. Okay, and so this is kind of a third proof that the harmonic series diverges. And everything is completely consistent with one another. And I might as well get out of the way here. One of the facts that I seem to talk about for absolutely no good reason for lots of time, back in section 7.8. So section 7.8, we saw that the integral of 1 over x to the p from 1 to infinity converges if and only if p is bigger than 1. Right? If you remember, we spent lots of time talking about this, and it might have seemed strange at the time, but the reason is for the integral test. It turns out that what this means is that the sum of 1 over n to the p, as n goes from 1 to infinity, converges if and only if p is bigger than 1. And so if p is equal to 1, this diverges. It's the harmonic series. If p is equal to 1/2, it diverges, because that's less than or equal to 1. But if p is equal to 2, right, if we have 1 over n squared, or 1 over n cubed, or 1 over n to the 1.01, that series is going to converge. Okay, and so this is one of the big results that we get from the integral test. Okay, these series are called p-series. Okay, so a p-series is exactly a series of this form, 1 over n to the p, as n goes from 1 to infinity. And now we know everything that there is to know about these. Well, that's definitely not true. But we know exactly when these series converge and when they diverge if we think about p as being either bigger than 1 or less than or equal to 1. So, for example, if I were to look at the sum from 1 to infinity of 1 over n to the e, this converges. Okay, so no questions there. E is 2.718, that's bigger than 1. If I were to look at the sum of n to the 1 over pi, as n goes from 1 to infinity, this diverges, right? 1 over pi is less than 1, okay? And really, that's all that there is to this. That's really all there is to this. So we have n to the 1 over pi. 1 over n to the 1 over pi diverges because that exponent 1 over pi is less than 1. Okay. The integral test can also be used for a few other things. So if I wanted to look at the series of n over e to the n, okay, something like that. So if I wanted to look at n over e to the n, as n goes from, say, 0 to infinity, we would compare this to the integral from 0 to infinity of x over e to the x. Okay, and what we could do here is we could evaluate this integral, and if we wanted to be very careful, we could evaluate this integral by parts. We could find out what the value is exactly, but notice that we don't care what the value is. All we care about is whether the integral converges or diverges, and hopefully we know that x over e to the x goes to 0 so rapidly because e to the x goes to 0 very, very rapidly, and that's in the denominator. And so this is going to converge, so this converges, and therefore this converges. Actually, we're going to see later in Chapter 11 how to evaluate this series explicitly. I'm not going to ruin it now, but we'll see when we talk about something called power series. So in section 11.8, we'll talk about how do we evaluate this series exactly. Okay, so that's something that we're going to be looking at soon. Okay, one or two more examples. What if I were to look at the sum of 1 over n natural log of n? Here, n can't start at 1 because we'd have a 0 in the denominator, but let's start at 2. So if the cutoff is 1 over n to the p, where p is bigger than 1, this looks like this is a little bit bigger than, this is kind of like 1 over n to the p, where p is something that's a little bigger than 1. But it turns out that this is going to diverge. So we're going to compare this to the integral of 1 over x natural log of x from 1 to infinity. This is the limit as n goes to infinity of the integral from 1 to n over 1 over x natural log of x. We substitute u as natural log of x. du equals 1 over x dx pops out of that. And what we end up with is the limit as n goes to infinity, so that part's the same, of the integral from 0 to n, 0 to the natural log of n. So when x is equal to, I'm going a little quick here, when x is 1, u is 0. And when x is n, u is the natural log of n. And this is going to be 1 over the natural log of x dx, so 1 over u du. And it turns out that this is going to be the limit as n goes to infinity of, let's see, we're going to have the natural log of u as u goes from 0 to the natural log of n. And I'm sorry, what did I do here? I have a problem because I wasn't paying attention and I started the series. I started the integral at 1, but it can't start at 1, it diverges. there. So anyway, so this should be not 0, but the natural log of 2. That makes me a little happier. That makes this the natural log of 2. And so this is going to be the limit as capital N goes to infinity of the natural log of n minus the natural log of the natural log of 2. And the natural log of the natural log of 2 is just some number. But think about what happens here. As n goes to infinity, natural log of n goes to infinity. And as this inside goes to infinity, the natural log of whatever that infinite inside is going to be also goes to infinity. So this is going to be plus infinity. Okay, so it turns out that this integral diverges, and therefore this series diverges. Okay, and we'll do some more examples as we go along.